Okay, so last lecture we examined the relationship KFF, structure stiffness matrix, sum E equals 1 to the number of elements, NEL, right? ABFE transpose, KE, individual element stiffness matrices times ABF for element E. Okay, so this is sort of a, this expression comes out of a theoretical analysis, okay? So it's good to show theory. Okay? Also notice, right, because K is symmetric and you have this transformation where you pre and post multiply by something and something transpose, right? The end result needs to be symmetric as well, right? So the structure of the stiffness matrix shows symmetry of KFF, okay? Right. However, as we discussed last time, this is not what's used in practice, okay? And so what is the algorithmic counterpart? Okay. Right, so algorithmic counterpart is as follows. Okay. First, right, because KFF is a sum, and you can imagine that you go element by element in the structure and populate the stiffness matrix, you need to initialize it to 0. So this would be the sort of the initialization part. Okay, very important. Okay. So now that you've initialized things, okay, then you can foresee some kind of a for loop, right, where you loop over all the elements for E equals 1, right, to NEL. So here you have loop over elements. Okay. And then for every one of these elements, supposedly you have a procedure that you've implemented in the computer that gives you the element stiffness matrix. Let's call this guy Gen KE. Okay. And to this one, you'll feed the element number. Okay. You will feed the element coordinates. Okay, let me just call it X sub B. Right. You will feed the area, and you will feed in material property, okay? And you will get back KE, okay? So this is your input, right? Element number, geometry, and material parameters. And your output is the corresponding stiffness matrix, okay? And so now you have KE, and your job is to now populate KFF, okay? So algorithmically apply these transformations by BF, okay? And so as far as sort of pseudocode is concerned, it's actually much simpler than you think, okay? So what you need to do, right, is you need to loop over, right? So you isolate each individual stiffness matrix. Now you need to loop over the degrees of freedom. And you need to do it for each row and for each column, right? So you can imagine there's another for loop where some index I goes from 1 to 4. And this is a loop over element DOFs, okay? And then you have another index for J equals 1 to 4, okay? And also loop over element DOFs. DOFs, okay? So now once you're inside that loop, right, you need to populate KFF. Okay, you do it entry by entry, KFF. Okay, and here's where the ID array is used. You use ID, right, of what? Element E and local DOF I. Okay, this should give you a global row number of the matrix. Okay, ID of JE. Okay, this will give you a global column number equals to whatever is in that entry already, ID IE, ID JE, okay, plus KE IJ. Okay, so you take the entry of IJ of the local stiffness matrix KE, okay, and you add it to the corresponding global entries of KFF using the ID array. So it looks as simple as that. Okay, so you conclude your and 4, and 4, and then and 4. And so this is sort of what your pseudocode looks like for this case. Okay, and this can handle an arbitrary number of elements, provided that you have the ID arrays, you know how to compute local matrices and so forth. Okay, so now let's revisit our example again. Okay, if you recall, this was our element A, this was our element B, right? This was our node 1, this was our node 2, this was our node 3, right? These guys were restrained, and there was a P equals -9. Okay, applied at this at the node there. Okay. So let me take you through, right, the stiffness matrix assembly. Okay, and then we'll go from there. Okay. So let's start with element A. Okay, and here I urge you to look at the nodes. Okay, to recall some of the entries of the different matrices that participate. Okay, so let's start with gamma ROT. Okay, equals 2. Right, remember, cosine sine minus sine cosine 0 0 0 0 0 0 0 0 cosine sine minus sine cosine. Okay, the element was flat, right? So our cosine was 1, our sine was 0. Okay, and if you plug in the entries, you get 1 1 1 1 on the diagonals, right? Zeros everywhere else. Okay, and gamma ROT for element A becomes an identity matrix. Okay. Gamma RBM is element independent for a truss, is always this. Okay, and if you recall, we assumed that our basic stiffness was directly given numerically. Okay, 300. Okay, it's a 1-by-1 matrix, and corresponds to the ratio of EA over L. Okay. So this allows us to compute Ka directly from the formula we developed. Gamma ROT A transpose gamma RBM K prime gamma RBM and then gamma ROT for element A. Okay. Right. So you have 1 1 1 1 zeros everywhere off the diagonal, right? Gamma RBM transpose is -1 0 1 0 like this. Okay, this goes and multiplies 300. Okay, this goes and multiplies gamma RBM. Okay. Minus 1, 0, 1, 0. Okay. And then that multiplies gamma ROT, which in this case is an identity. Two zeros on the diagonal. Okay. So if you carry out this product, okay, you find that the matrix equals to 300, 0, negative 300, 0, 0, 0, 0, 0, negative 300, 0, 300, 0, and then zeros here. Okay. So in fact, as you expect, a symmetric 4x4 matrix. Okay. Right, we derived the idea raised for element A already, so let me just put it on top right away. 0, 0, 1, 2. 0, 0, 1, 2 on the side. Okay. Then we ignore this row. We ignore this column. Okay. All that's left is the bottom 2 by 2. Okay. And then the only non-zero entry from the bottom 2 by 2 is this 300. Where does it go? Into KFF 1, 1. Okay. So KFF move the f's upstairs, 1, 1 equals 2. Okay, whatever was in it, we initialize it with what was 0. Okay, plus 300. Okay, all the other entries stay the same. Okay, and they're 0. Okay, let's go to element B. Okay, remember this is the element that comes at an angle. Okay. So we again compute gamma ROT. Okay, and we find, right, that if you evaluate the expression like this, cosine, sine, minus sine, cosine, right, you'll find that the entries, and remember C equals, right, delta x over L, sine equals, in this case, delta y over L. For this case, equals to 0.8. Okay, and then sine equals to 0.6. Okay. So then the gamma ROT actually is like this: 0.8, 0.6, minus 0.6, 0.8, 0, 0, 0, 0, 0, 0, 0, 0, 0.8, 0.6, minus 0.6, and 0.8. Okay, gamma RBM as before. RBM as before. Okay. Right. Again, for simplicity, I assume that KB is 300. Okay, in the appropriate units. Okay. And this allows me to compute K sub B directly. Okay. Equals to gamma RBM transpose, which is 0.8 minus 0.6, 0.6, 0.8, 0, 0, 0, 0, 0, 0, 0, 0, 0.8 minus 0.6, 0.6, 0.8. Okay, watch the signs, right, on 0.6, because of the transpose, the off-diagonal entries flip, right? That guy goes and multiplies RBM, which is unchanged. Okay, then this guy goes and multiplies the basic stiffness. Okay, followed by post-multiplication by RBM, minus 1, 0, 1, 0. And then by gamma ROT itself, which has the original entries 0.8, 0.6, minus 0.6, 0.8, 0, 0, 0, 0, 0, 0, 0, 0, 0.8, 0.6, minus 0.6, 0.8. Okay, so at that point, you probably want to invoke your favorite package, like MATLAB. Okay, and if you carry out the computation, you do get that KB equals 2. And then you do get nice round numbers, 192 144 minus 192 minus 144, 144, 108 minus 144 minus 108 minus 192 minus 144, 192, 144 minus 144 minus 108, 144, and 108. Okay, again, you get a symmetric matrix, right? Also notice that every row sums to 0. Okay, what this means is if I apply the translation to this bar, okay, then the forces will not develop. Okay. Next, I put the ID array 0, 0, 1, 2. Okay. I put another one 0, 0, 1, 2. Okay, remember this was ID for element B. Okay, so this allows me to wipe out 2 rows that are irrelevant, right? And here's my 2 by 2 block, okay, now expressed in terms of the actual numbers, right? And so this tells me that whatever was in KFF 11, right, gets added 192, right, from here. Whatever was in KFF 12 gets a 144. Whatever was in KFF 21 gets a 144 plus 144, and whatever was already in KFF 22, right, gets a 108. Okay. Now, what do we remember? From element A, right, KFF1 was already 300. Okay, so the end result is 492. This is from element A. Okay, so you see how the elements couple together to produce the entries of the structural stiffness matrix. KFF12 was 0, so all I get is 144 here. Right? This was 0, so all I get is 144 here, and K22 was also 0. Okay, and all I get is 108. Okay, and so now we're actually done with the computation for KFF for this case. Okay, we get 492, 144, 144, and 108. Like this. Okay. Right. So where do we go from here? Right. From here. Well, if you recall our example, right, we had a force of -9 acting in this direction, right? What was that direction? This was U1, and then the corresponding applied force P1. This was U2, and the corresponding applied force P2. Okay? We're specifying a vertical force. We're not specifying a horizontal force. Okay? So it says that P1 is 0. I am applying a force, but that force is 0. Okay? You always have to apply something at the free node. Okay? If you apply nothing, it means you're applying 0 force. Okay? And then P2 becomes -9. Okay? Recall that this was our PF. It was P1, P2 like this. Okay? And now I have a system to solve. Right? KFF times UF equals to PF. To make the subscripts consistent. Right? KFF I just derived, 492, 144, 144, 108 times U1, U2, okay, equals to P1, which is 0, and P2, which is minus 9. Okay. Right. And now this allows me to actually solve for the 3 degrees of freedom. Okay. So UF equals to KFF minus 1 times PF, right? Inverse of the stiffness matrix times the applied forces. Okay. Is KFF minus 1 times 0 and minus 9. Okay. So you can do this by hand for a 2x2 maybe, you don't want to go beyond that. Or you can do this in MATLAB, right, which you'll be doing later in the class, where you can say UF is KFF backslash PF. Okay, this would be the MATLAB command. And backslash will pick the best way to solve the system. Okay. And so if you carry out that operation, what you get is something that looks like this, plus 0.0400, okay, and minus 0.1367. Okay, 367. So what this analysis tells you, right, is that if this was your undisturbed, right, configuration, right, and then you applied a force P equals minus 9, right, to the to that structure with these given dimensions, okay, and I believe this size was 6 and this size was 8. Okay, you would see a fairly small displacement of that node, but let's exaggerate it. Okay, it actually moves to the right and it moves down. Okay, so the new location would be somewhere here. Again, exaggerated. Okay, you can see that 0.04 is a very small fraction of 8. So you probably don't see it with your naked eye, which is a good news, because if you do see a displacement clearly, then probably linear analysis doesn't apply. Okay, but for the purposes of that class, this class is sufficient. Okay, you get something that looks like this. Okay, so this becomes your deformed configuration. Okay. And so again, it's interesting if you look at that solution, right, you apply a vertical load like this pointing down, you would expect this node to displace down, right? But, if you don't have much experience with problems like that, right, you probably wouldn't have guessed, right, that the node moves to the right. I mean, some fraction of you would have said it would move to the left, right, if you were to just do things intuitively. Okay? And so here everything is nice and rigorous. So at this point, right, you've basically assembled your stiffness matrix, you're given some force, and you find the displacement, right? So this is good. You've done the bulk of the work, okay? But this is things don't stop here, okay? And so the next step is, right, once you have a solution, UF, right? Oftentimes, it's not the displacements that matter, okay? It's how that applied force distributes through the different structural members, right? And whether these structural members are able to take this type of force without buckling or failing in some other fashion, okay? So the next stage is, once you have the solution, right, you carry out what's called element state determination. Okay, or post-processing, as the procedure is commonly called in finite elements, sometimes also referred to as stress recovery. Okay, and so in this model, you want to determine forces in each element. And direction of those forces. So basically you want tension or compression. And by how much, okay? And the second point is that you want to get forces at support reactions. Supports, okay? So basically you want to know what's happening with this element here, with this element there, whether it's in tension and in compression, what's the magnitude, right? And then what are the forces that are developing in the supports? Okay? Because again, the supports are designed in a certain way, and they're designed to take a certain amount of force. Okay? If the computed force exceeds what they're designed to do, then you have to go back to the drawing board. Okay, and so how would you do this? Okay, well, you work backwards. So you have your UF, okay? Then from UF, right, you need to extract delta E, right? All the element displacements, okay? And something like this, the easiest you can do is use the ID array. Okay? So let's look at element A, right? Delta A equals 2. Right? So what was our ID for A? 0, 0, 1, 2. Right? So when you populate delta sub A, right, you know the first two are restrained, so nothing there. This has to be U1, this has to be U2, according to the ID. Okay. Right? So if you focus on the solution here, right, you find that this is 0, this is 0, this is going to be plus 0.0400, and this is going to be minus 0.1367. So this is the displacement state that the element A will see. Okay? Right, so now you know the displacement state. What do you need? Right? Then you need to compute for element A its basic displacement. Right? And there you just apply the formula that we have developed in class. You get gamma RBM and gamma ROT for element A times delta A. Okay? So first operation will effectively take the global displacements and convert them to a local coordinate system. Once they're in the local coordinate system, gamma RBM subtracts everything away and just keeps the basic displacement, right, as we've seen. Okay? And so what you find is you get plus 0.04, okay, if you do this multiplication. Okay? And so now you can compute the basic force. It will be the basic stiffness, right, EA over L for element A, right, times delta for element A, right, this is 300, times 0.0400, right, you get plus 12, okay. So this is going to be, right, units of force, right? And because this is plus, it's tensile. Okay. So the element develops tensile force of 12 units of force from this analysis. Right. So now we can do the same for element B. Element B. Okay. So we populate delta B, right, from the ID array. Right. ID for B was also 0, 0, 1, 2. Okay. Which means that delta B is 0, 0, U1, U2. And in terms of numbers, you get 0, 0, plus 0.0400 minus 0.1367, like this. Okay. So you get the basic displacement again, right? Gamma RBM, gamma ROT, B times delta B, right? So in this case, minus 1010 times 0.8, 0.6 minus 0.6, 0.8, 0, 0, 0, 0, 0, 0, 0, 0, 0.8, 0.6 minus 0.6, 0.8. Again, don't recommend you do it by hand, right? You can do it all on the computer. Right? You stick in 0, 0, 0.0400 minus 0.1367. Okay, and so once you carry out that multiplication, you get minus 0.05. Okay. Computing the basic force for element B, right? EA over L for B times minus 0.05 is 300 times minus 0.05. I get 15 negative units of force. Okay. So element is in compression. Well, relatively shortens and develops compressive force of 15 units. Good. Okay. Right, next. So this is how you handle the individual elements. So how about PD? Right? Forces at restrained DOFs. All right. So remember, right, that those were computed like this, right? Sum E equals 1 to NEL, right? A BD E transpose, right, times FE. Okay. So you basically need, right, extract from the displacements, right? You would need to extract the element force, okay? And then, once you do that, you use the Boolean matrix, right, to place it in the correct location of PD. And then you add the next element, the next one, and you build it up this way, okay? Right. If you recall what FE was, right, you would start with a basic force, pre-multiply by gamma RBM transpose, right, to get it into a local coordinate system, and then multiply by gamma ROT transpose for that element to put it in a global coordinate system. Right? So you work your way, right, So you've done the element state determination, right? You determined what f prime over bar is for each element, and now you kind of build it back up from the basic system to the local, to the element global, to the structure global. Okay? And so for our case, right, what do we get? Sort of formally. If you look at your notes, you get 1, 1, 0, 0, zeros off the diagonal, right? This was our A, B, D transpose for each element. Okay. Gamma ROT for the first element was just an identity, 1, 1, 1, 1, 0, 0 here. Okay. Gamma RBM transpose is minus 1, 0, 1, 0. Okay. And this whole thing multiplied the basic force for the first element, which was plus 12. Okay. So this is contribution from element A, right? And then plus contributions from element B, right? You need to sum them all together. Okay. So if you recall from the notes, the Boolean was like this, 1, 0, 0, 0, 0, 1, 0, 0. Okay. Here you have to use the rotation, 0.8 minus 0.6, 0.6, 0.8, 0, 0, 0, 0, 0, 0, 0, 0. And you repeat, 0.8 minus 0.6, 0.6, 0.8. Okay. Minus 1, 0, 1, 0. And this thing multiplies the force in that element, which was, let me write it here, remember, minus 15. Okay. And so this becomes ABD, 1, and this is 1, right? ABD, right? Transpose for element B. And so then you see that element 1 contributes minus 12, 0, 0, 0, okay? And element B contributes nothing here, right? Everything's consistent, plus 12, and then plus 9, okay? And this is exactly P3, P4, P5, and P6. So if we see our structure, element A, right, remember, develops tensile forces 12. Okay. Here is the node. Okay. You see equal and opposite action, 12, right? You see the applied force of 9 in the negative direction, right? Call it minus 9. Well, right, the applied force of 9, okay? Applied force of 0. Okay, this is 12. This is our support. Okay? You have equal and opposite acting on the element of 12, right? And then you have some P3 here and P4, right? Support reactions. Okay? That from the above analysis says that P3 equals to minus 12, right? And P4 equals to 0. And here you have a constant state of tension, right, where that equals to 12. Okay. Then you have element B, right? This guy is in compression, constant state of compression, minus 15 units of force, okay, means that the end forces are like that, 15, 15, right? Then we have equal and opposite action. These guys are 2, right? 15, okay? And as before, we have 9 pointing down, applied 0 here. Here we have node 3, right? Equal and opposite action. Then we have P5, which according to our analysis is 12. And then we have P6, which according to our analysis is plus 9. Okay. And as you can see, everything is in equilibrium, right? So let's look at node 2. Okay. Right. And let's collect all the forces that are acting on it. You have 9 going this way, right? 0 going this way, 12 going that way, right? And 15 going this way. Right? So if we look at sum fx, I get minus 12, right? Plus 15 times the cosine of the angle, which is 0.8, okay, I get exactly 0. Okay. So clearly this node is in balance in the x direction. Fy, I get minus 9, right, plus 15 times the sine of the angle, which is 0.6. I also get a 0. Okay. So you can see that our structural analysis procedure gave us the force equilibrium at this node. Right? Okay. Let's look at node 1. So in the x direction, right, I have 2 forces acting. Plus 12, right, from the force that's developed in the structural member, and minus 12, which is P3, equals 0, which is exactly the sum forces in the x direction here. Okay. And then sum f of y, right, if you look here, P4 is 0, right, and the element only exerts forces in the horizontal direction. So 0 plus 0 equals to 0. Okay. So you see equilibrium is satisfied at node 1, right? So our structural analysis procedure using formal operations actually found for us, right, a state, right, of support reaction that puts that node in equilibrium with a force that's acted upon it by a deforming structural member. Okay? And so if you look at the node 3, right, you're seeing the same thing, right? You have minus 15 times cosine of the angle, which is 0.8. This is coming from the structural member, plus what the structural analysis procedure produced for us, P5, which is 12, equals to 0, right? So then sum fx is satisfied. Okay. And then in the vertical direction, okay, sum fy equals minus 15 times 0.6 plus 9 also equals to 0. Sum fy satisfied. Okay, so you see, rather than trying to extract what the support reactions are by going at each node and then sort of writing down the equations of equilibrium, you actually use the matrix sort of structural analysis procedure, just formally applying the operations. For every element, you go from the basic force all the way to the global force. And you obtain exactly the force reactions that you're looking for. Okay? And so that procedure, okay, is known as the post-processing. Right? And now you can make statements that, is the element strong enough to be able to sustain that much force and tension, that much force and compression, and other supports built sufficiently well in order to sustain, the corresponding forces that develop. Yeah. So that's where the questions are. Okay, I'll stop here.